Hi, Nicola.
Hi, I'm Nicola Potts. I'm a first-year PhD student at the Open University, using Lunar Apatite to assess the volatile imagery of the lunar interior. If we'd been talking about the volatile imagery of the lunar interior in the Apollo era, we would have been saying that compared to the Earth, the Moon is depleting in volatiles. And as we've heard from Lindy and from Jess's talk, there's been a lot of work recently that's been on looking at volcanic glasses and looking at lunar apatite, and they've been finding quite high concentrations of OH in these samples. As we heard on Tuesday as well, we also have spacecraft which are detecting OH and hydrogen on the lunar surface. Sorry, bear me a second. My screen's over. So I'll just move on to the apatite rather than repeat what everyone else was saying. Apatite is a calcium phosphate mineral. It's an accessory phase mineral that is found ubiquitously in lunar samples, and it's the main carrier of volatiles in lunar rocks. Initial measurements of apatite use the electron microprobe, in which chlorine and fluorine contents could be measured, and having the measurements of chlorine and fluorine, they could calculate the OH measurements in the apatite. There are a few hiccups of this, or a few caveats of measuring apatite via the electron microprobe. Apatite actually can take in pretty much any element into its crystal structure, so by assuming that the gas filled primarily with OH might lead to some overestimates. You also have issues with the crystal structure in that you can't have fluorine and chlorine sitting next to each other. They don't like to do that. And there is some uncertainty in measuring the fluorine on the probe. So some of these original estimates were then verified by the ion microprobe, but we've been really fortunate here at the OU in that we have NanoSIMS, as Jess was saying, and we've been able to now start getting some accurate and precise OH measurements and delta D measurements for the Apollo samples. So this graph is the work that's been done on Mare basalt by Roman Tortes, who's a postdoc in the group here. And we've just seen the results that Jeff got for the Highland samples. So you can see we're seeing quite a variety of OH and delta T signatures, and something that the group here has been working on is looking at the sources of hydrogen into the lunar interior. But something I specifically want to look at is modelling the magmatic water content of the magmatic source regions. So to do this, we can look at the measurements of water in apatite and try and back calculate how much water would have been in the melt at the time that apatite formed. Unfortunately, we don't, we don't really have any well-constrained accurate partition coefficients for apatite, which is one of the big caveats of this model. So for apatite partitioning, the work that's been done previously has looked by Perot and Clem. They were looking specifically at rare earth elements, and they found quite a strong melt composition dependence. The work by Mattei and Webster, they, like Perot and Clem, were looking at a terrestrial system. They were looking specifically at the Stillwater and Bushveld complex, which is a highly saline complex. They were looking at chlorine and fluorine partitioning, but they were using quite a low pressure and relatively low temperatures. What they did find, though, was there was a really strong composition dependence for chlorine, but they didn't really find much composition dependence for fluorine, apart from a weak one with calcium oxide. So we know that there is a composition dependence for apatite partitioning. So we want to look specifically at lunar conditions and lunar melt composition. And I've been starting to do some experiments for University of Amsterdam using a piston cylinder apparatus with a talc pyrex assembly. And the parameters that I was specifically interested in are temperature, pressure, melt composition, and oxygen fugacity, all under lunar conditions. The initial experiments that we've begun have been using a terrestrial basalt composition, which is similar to one stated by Perot and Clem in their 2006 paper, and it's a pure fluoroapatite end-member composition. The run conditions were we had a liquidus of 1350, a pressure of 1 gigapascal, and we ran the temperature for 5 hours at 1250. We also did another experiment using the exact same conditions, but left that one for 20 hours to ensure that we had equilibrium conditions. The samples have then been measured on the NanoSIMS. The samples have been measured on the NanoSIMS, which is, as Jess was saying, a secondary ion mass spectrometer. We use the cesium plus probe, which bombards the crystal surface, and then we can measure the secondary ions which are released from this. We pre-sputter the surface before measurements to remove any contamination, and we've been using it in imaging mode due to the size of the apatite crystals. One thing that we aim to do is that the experimental samples that we've been measuring, we hope to measure some natural samples as well so that we can have consistency in the measurements that we've hope to achieve. So we've initially just been making a protocol for measuring chlorine and fluorine abundances in our glass in the experiments and also in the standards. We make a standard calibration from known fluorine and chlorine content in the glasses, and then we are able to move any background. We've been getting some good results from this. We calculated a precision better than ±5%, and most of that error being within the standard measurements, not actually from the NanoSIMS. So moving forward with this work, now that we have a protocol for measuring chlorine and fluorine in the glasses, we want to start measuring them in the apatite standards, which we've got from Francis McCullin, and also in the experimental apatite. And then obviously we'll be doing more experiments. The initial experiments that were completed were, as I said, pure fluoroapatite, and no chlorine or OH was added, but we are seeing a background of around 46 ppm chlorine, which indicates that the pure chemical reagents that we use probably have a little bit of chlorine contamination. So we want to be able to make sure that we can remove this background when we start looking at partitioning along the 4OH binary. And we're going to combine this with measurements of chlorine and fluorine abundances in samples that have already been measured for OH by Roman Cortez. And these are also the same samples in which he's measured delta D signatures. And also we want to start measuring fluorine isotopic signatures for these same samples so that we have the full speed. When we have the full chemical abundances in the Apollo samples, we can combine that with the experimentally derived partition coefficients to create a more accurate model on water abundances in the magmatic source region, specifically the lunar mantle.
Thank you, Nicola. We've got a question from Rishitosh. The range of OH for a single sample is huge. Are those measurements of a single grain of apatite or more? And if it's a single grain, what is the cause of such variation?
Sorry, I didn't hear the question originally. I'm just reading it now.
So the range of OH in a single sample is huge, and they'd like to know if that represents a single grain of apatite or is that multiple grains?
Oh no, it's several grains. Sorry, several grains of apatite. Does that answer the question?
That answers their question. Are there other questions for Nicola? Somebody's typing.
We can continue questions in the chat area, and we can move along to the next speaker if you'd like.
Thank you, Nicola. We'll move on.